Hi guys, here we are in another glorious week of lockdown. I'm following on from a puzzle I set over the weekend. If you haven't done it, I suggest you pause right now and go and have a look at it, see if you can actually solve the problem with the pieces of paper. That was really a starter for this session. Okay, now you're back. You have access to the discussion I went through with you on my solutions. There's quite a few solutions you can make for it. There's the one I showed you where in the square, if you put, if I remember, yeah, if you put in the right angle so it's partway along, you get a whole series of intersections where you get a small square in the middle, 4 triangles around the outside. That one I showed you. You'll get loads of different ones where it doesn't matter what your organisation of the triangles are. So they may even actually make a square like that, but you can actually end up making smaller and more, lots of smaller squares, so that eventually it creates a series of squares. They're not the interesting solutions. We're not looking at those. There's basically 3 solutions that we're looking at. One that is pretty much unique, and the other 2 are related. And the reason they're important is they've got the additional property that the outside shape is actually the same size. So what we're looking at are, and I'll just do a quick sketch and then I'll show you better in GeoGebra. The first one is if you put a point partway in, so your triangle cuts into there, then the next triangle joins onto the end of it, the next triangle onto the top of that, and the next triangle there. We've got 4 identical triangles and a big square in the middle. You then have 2 other options. I'll show you the second option, the one that I'm not going to be using, where you can put 2 triangles together, like that, and then if you put them, turn exactly the same thing and turn it through 90 degrees, we can actually create 2 squares which are exactly the same. And what's big about this is these 2 squares and these 4 triangles take the same space as that square and those 4 triangles. So here's a GeoGebra image for it, for the second version of this one. Notice instead of putting these 2 on top of each other, I've just taken these vertical ones and put them on the other side, and now you've got 2 clear squares. Now, the reason people like this one, if you look at this triangle and watch what happens when I translate it and slide it onto the next diagram, that shows these 2 triangles are the same. Okay. So if I now start doing an extension and extend it from there, that's why they were doing that. What I can do is I can also slide the squares and then create a third diagram. So the blue square goes onto the long side of the triangle on top. The rest of the diagram is actually basically a copy of these 3 elements, the 2 squares here and that triangle. So I'm going to take a copy of that picture and put it into my notes. Okay, so I've created the 2 bisections using 4 triangles and then rearranging everything so that it all joins onto the one triangle. So these 3 parts all stay in the same place, and this big blue square goes onto that side. Now, there's some very special things to note. First of all, the triangle is right angled because it makes a square in the corner. It's because of that, and that these 2 big squares are the same, that allows us to lead to the special result. The other part is, because there's a right angle in the triangle, we need to label our triangles carefully. So I'm going to put a diagram below, which is a triangle with a right angle. In fact, I'm going to try and draw it properly. So I'm going to create a right angle like that. Make it right. Draw another triangle on it. And normally we label sides using lowercase letters to show length. Okay, capital letters show points. Lowercase letters normally use are sides. Now, I'll label these two A and B. If you use letters in sequence, that just means that those two shapes actually have the same sort of properties. They're similar to each other. And what it means in this case is A and B, doesn't matter which way round they are, but they are related to each other by the right angle. Now, some formulae, particularly Russian books, label this one C. Now, I disagree with them because C is not just a special one. You can't swap it with A and B as you feel like. It is a special side, and it's a special side because of the right angle. So the right angle tells me that the opposite side is what's called the hypotenuse. And I quite often make a mistake with this, so I just want to check it. Just checking the spelling. There's an extra E in there. I do it quite often. So hypotenuse, it's just a U. And that's a special side. It is by definition the side of a triangle opposite a right angle. So if we look at the red triangles in our diagrams, and let's label them in the same way. So that's side A, side B, and side H. Side A, side B, side H. Side A, side B, and side H. Now, we'll have a look at these squares now. The blue square, because it's on side H, I'm going to say its area is capital H. This green, because it's on the same side as my A, I'm going to label it as capital A. And the small square, capital B. So we actually have, got these the wrong way around, A, B, and H. Just correct my notes here, A and B. Now, because of the way this is all set up, hopefully you've all realised there is a relationship between this square and these two squares. I'll give you a moment to think. And hopefully, yes, you should have realised, because these are the same size squares in the red area, the red squares are equal. I've taken away 4 triangles in both cases. The area shape H must be equal to the area of A and the area of B. So now I'm going to move on and think, okay, what else can I do with this? So we've got the area of the square H. Well, how can I calculate that square H? Well, the square H is the little h times itself, H squared. I've got the square A. How do I calculate the area of A? Well, A is A squared. And I've got the little square B. How do I calculate the area of the square B? That's B squared. That has given you one of the world's most famous formulae. The square of the hypotenuse is equal to the square on the other two sides of a right angle triangle. So H squared equals A squared plus B squared. Now, I'm going to set you challenges that involve using that formula in all ways round. I don't see the benefit in learning special cases. Let's just learn how to manipulate them and work with them. Friday, there's a thing called Pythagoras Triples, and we'll be looking at them. They're special numbers. Now, you're going to see a few of them today as I do these questions. So the question is, I'm going to draw a triangle. I'm going to tell you some of the sides. Let's say that's 12, and say that one's 5 centimetres. And the right angle's at the top there. So the question I'm being asked is to calculate the side on the bottom here that they might call A. They might call it something like that. I'm going to relabel everything in my own way. So we start off, the important side is the side opposite the right angle. Opposite the right angle is the hypotenuse. So instead of A, I'm going to call it H. The other two sides on the legs that are next to the right angle, it doesn't matter which way round they are. I can call them A and B. First step, think of the equation h squared equals a squared plus b squared. This line I wouldn't expect to see all the time. I wouldn't expect you to always rewrite Pythagoras theorem. It doesn't always give you the marks to show Pythagoras theorem itself. So that bit is optional. But what I would expect to see is what it becomes when you replace all the letters with what's in the diagram. So my H has become their A. So the stuff I'm writing in green is my solution. So A is equal to my A, which was 5 squared, plus B, which is 12 squared. Now I deliberately chose to use a nasty name here because it's one of those things that examiners do quite a lot. And I'd rather you saw it quite early on and got used to it. It's not a special case, it just happens quite a lot. So their diagram is what I'm writing in green. My relabeling is what I'm thinking, and that's in blue. So I'm relabeling my diagram to say where A, B, and the hypotenuse H is. That's the important one to get right. Where is the hypotenuse? Now I can go through and try and solve the problem. A squared is equal to, and this is where I'll bring in my calculator. So I'll bring my calculator in, and to calculate A, I need to do 5 squared plus 12 squared. So 5 squared button, I'll press the square button, plus 12 squared, and that will give me an answer, 169. So my answer to that bit is 169. But I don't want to know what A squared is, I want to know what A is. And the other big thing to remember is the opposite of squaring. So when we're doing solving equations, the opposite of add is subtract. The opposite of multiply is divide, or fractions. The opposite of square is square root of a number. They do the opposite things. So to get my answer A, what I want is to do the square root of whatever A was. So I'm now going to take the square root of the 169. Square root of my answer equals 13. Check my diagram. Yes, my units are in centimetres, so my answer should be in centimetres. So that's the first and one of the more simple ones. I'm going to give you another question. Notice the directions. What's going on? I'm going to tell you something weird. I'm going to tell you that this side is 5 centimetres, this side is 4 centimetres, and I want to know what the side down the bottom is. And I'm going to call it B for bottom. The right angle's in that corner, so we go through the same process. Thinking step. I would write these down if I did them. I always do when I'm solving these problems. First of all, put into the opposite corner the hypotenuse. Label the other two either way around. Well, because they called that B, I'm going to call that one B, and therefore that one is A. You don't have to write down the formula. I wouldn't expect to see it in a formula question, but for practice at the moment, maybe you'll want to. Then we go into the space, and we're going to do Pythagoras theorem. So now I replace, instead of H, what was H? H was 5. What was it in the diagram? A, what was side A? 4. And B, what's inside B? That's B. So my thinking, my theory, the actual problem is in green. Now I've got a weird thing. My unknown's there with some other calculation. So my first step is I'm going to take this to the other side. So I'm going to subtract 4 squared from both sides. 5 squared minus 4 squared. Well, I said I'm going to drag that to the other side to remove it. 4 squared minus 4 squared is nothing, so I can just leave that as b squared. Again, pull up my calculator, and this time I want to do 5 squared minus 4 squared. 5 squared minus 4 squared. That gives me an answer 9. And I just want to show you something that people get wrong quite a lot. Sometimes people will do what is 5 minus 4 and square it. They're not the same answer. It is each number squared. The other thing is, in a while, we'll start talking about distances between 2 points, and these distances can sometimes be negative, and therefore you should be putting brackets around them when they're negative. But that minus is because of the calculation. Back to what I did before. This little discussion here. I don't want b squared, I want to know what b is. So the step to go from b squared to b, I want to do the opposite of b squared. I do the square root of both sides. Now, this is a particular type of problem. Some of you might have come across this giving you 2 answers. Yes, there are 2 answers to a square root often, but in the context this is being calculated, it is only really a positive distance. The 2 distances would be equivalent. You've got a 3 and a minus 3, and that basically just says that if I come 3 this way, I can draw another triangle. But there's a lot of mathematics that would prevent me from actually saying it is the same. So, just digging through, we only need the positive answer. So my side B is 3 centimetres. Let's do one more with decimals. Give you a moment to think about it when I draw it. So let's put that there, that across there, and I'm going to give you this length here is 43.73 millimetres, and I'm going to say this one across here is 6.2 millimetres. What is this length over here that I'm now going to call x? So have a look at the question, think about the steps. What's the first thing I should do in my diagram? What should I be thinking about writing first? Okay, let's go through it then. My thinking steps, the stuff in blue. There's the rectangle, the right angle. So opposite the right angle is the hypotenuse. Relabel it. The other 2 sides are A and B. It doesn't matter which way around I call them. So I'll call that A, and I'm going to call that B. So now I need, what's the basic formula we need? Well, it's a thing called Pythagoras Theorem. Now, a little point for you. Pythagoras was born, I think, something like 500 years BC. The mathematics that's given his name has been known for thousands of years before. There's actually records of twine to make the pyramids based upon that last question. So I'll come back in a minute, I'll talk about this question and what the Egyptians were doing with this triangle. So let's continue the question. Replace each letter with the right number. So H is 43 point, oh, I forgot to do something in that question. Sorry, I'm just going to come back. That should be 6.6. I didn't realise before, I don't know. Sorry about that. I might go back and edit it. No, I'll show you the mistake. So this is 6.6 millimetres. Now I put my numbers in my calculation. So H is 6.6, and that's squared, is equal to A, which is x squared, plus b squared plus 6.2 squared. I want the x bit on its own. That's what I want. So I need to take this bit to the other side. As I take 6.2 squared to the other side, it changes from a positive to a negative. Do the opposite, it's a positive, changes to a negative. So I drag that to the other side and I get 6.6 squared minus 6.2 squared equals x squared. Now before we go too far, let's have a think. Oh, that looks like an incredibly small distance. It's hardly a triangle. You'll be surprised with triangles how small some numbers can be to make the side. So this turns around and says x squared is 5.12. It's my x squared. But, just like before, I don't want the squaring, so I need to do a square root to turn it into an x. So x, the square root of x squared is x, so I need to square root the other side. And the square root of the 512 is 2.26. Just realised I've done a load of stuff on a calculator without showing you. So I'll show you on here. We want to do 6.6 squared and subtract 6.2 squared. Oh, didn't get the 0.2 in. That gives me an answer of 5.12 squared. I want to square root. So I want to do the square root of that answer. That gives me 2.26. So 2.26, because this is in millimetres, 1 decimal place for a millimetre is probably a suitable measurement. So x is 2.3 millimetres long. That's it. You can go off and do the exercise that's been set. The little bit of history is when the Egyptians were building the pyramids, what they needed was, at the corners, they needed to find right angles. What they found was remnants of rope. The ropes actually were 12 units long, but they made a loop. Now if you take a rope that's got 5 units on that side, 3 units on the next side, and 4 units down the side here, what they've created is exactly this triangle. And the reason they wanted it was between the 3 and the 4 is a right angle. If you can make measurements, obey Pythagoras Theorem, you have proven that triangle has a right angle. Okay, so this bit uses that it's a triangle to solve the sides. But if you can actually create sides that obey Pythagoras Theorem, you get a right angle. Okay, off you go and do some work with them. I'll set some more questions tomorrow, give you another little bit of introduction. Thursday we'll probably be looking at something called Pythagoras Triples. They're just a nice pattern. And Friday the extension is actually quite a nice extension. You don't have to understand the proof, but it does have a funny relationship, and it's a bit like this diagram to do with the angle, but it's about creating a right angle down here on this hypotenuse as well. And it's called the inverse Pythagoras. It's a nice little Olympiad type thing that a lot of people use, and it actually is incredibly useful elsewhere as well. It's amazing how many people don't use it when they're coming to do mechanics. Right, off you go and do your exercises.